let's talk about electrical principles. And group B, one more question out of these. Current and voltage dividers, power, RMS, PEP, and decibels. You might need that. Yeah. Okay. Yeah. There's a thing called Kirchhoff's laws. He has a current law and a voltage law. His current law states that the sum of the currents entering a circuit node must equal the sum of the currents leaving the node. That's clear as mud, right?
Sounds more like Newton.
Well, he was a scientist, you know, they have to word things the way they do. Kind of like lawyer. So the total current in a dually resistive series circuit is going to be the same through each component. Doesn't matter how many of them there are, if they're all in series, the current is going to be the same through all of them, with the exception, there's a little thing in there that says purely resistive. Because if I've got inductors and capacitors in that series circuit, since they're frequency dependent, I can have currents that are out and voltages that are out of phase through the component, so it won't look the same as the current entering the circuit. So they condition it saying purely resistive. And we're not going to talk about any currents through LC circuits other than a tuned circuit. So the total current is going to be equal to the voltage divided by the total resistance in the series circuit. So you add up all the resistances and divide them into whatever the voltage is, and that's going to be the current in that loop. If you've got a parallel circuit, then the total current entering that is going to be equal to the sum of all the branch currents, one current through each leg. So it's going to be the sum of each of those in, because they're all going to have the same voltage since they're in parallel. So if they're different resistances, you divide that into the voltage and get the individual currents and sum them all up. But there's a very complicated drawing, but if you think about this one, okay, which is kind of a series parallel circuit, if I start over here, I've got these three resistors in this one leg that are in series. So the effective resistance in that leg is the sum of these three. Okay. And I know what, I actually don't know what the voltage is here yet, but I do know that I have an R equivalent of this in parallel to this one, so I can figure out what the effective resistance is of those two parallel. And then I've got another series, I add them up, okay, now I've got another parallel situation, which I can calculate. So I just kind of work my way back. You don't have to do this for the exam, this how you do this stuff in the real world. And you finally get back to where I've just got a simple loop. So you calculated the effective resistances of all those legs, work back. Each of these points here called nodes, or what he talks about in Kirchhoff's law of the current entering that node. So if I had a current coming in here, okay, the current going this way and the current going that way will equal current coming in. So it has to add up to zero. And likewise, his voltage law, which we didn't talk about, says when you go, the voltages around the loop will equal zero. So if I start up here, okay, I've got a voltage drop across this resistor that's pointed in this direction, plus this one, plus this one. So I have these three voltages. When I come over here, I've got this one in the opposite direction. So this voltage is going to be equal to the voltage, the three voltages here. So it will add up to 0. So the voltages around the loop always add to 0. The current in a node always adds to 0. There's just another one showing a node with a lot of ins and outs. Voltages around the loop or the current. And here's an example of calculating the branch currents in this parallel circuit. So you know the voltage across each one. So the current for each one, you add them up and you get the total amount of current into the loop. So, oh, I didn't see. Amanda made it. Hello, Amanda?
Yes.
Yeah, I heard.
Can you hear me?
Yeah.
Awesome.
Did did the time difference mess you up?
Oh no, is it not 9:30 in Florida?
No.
Oh no, what time is it in Florida?
10:30.
Oh
10:38.
no. Okay. Yeah, I messed that up. I won't mess it up next time. I'm sorry about that. I didn't mean to interrupt.
Right. Well, you didn't miss too much. Well, at the end, I'll go back over some stuff if you got questions.
Great. Thank you.
Okay. Okay, so how does the total current relate to the individual currents in a circuit of parallel resistors? H. C is in Charlie? Yep. Yeah, use phonetics. I'm hard of hearing.
I understand that. Well, I'll just flash like I do with Mike.
Right. The sum of the currents through each branch. It's not the average, A. It doesn't decrease, it stays the same. What decreases when you add more parallel branches is the current in each branch. And it's, let's see, the sum of the reciprocal of each individual voltage. No, it's not that one either. Okay. Sine wave, root mean squares. This only really applies to sine waves. If you have a triangle waveform or a square waveform or some really odd waveform, the numbers don't work the same. And you don't have to do the other ones on the exam. So for an AC sine wave, the RMS value is the value that creates the same amount of power dissipation or heat as a DC voltage at the same value. So when in your house you've got approximately 120 volts AC, that's 120 volts RMS coming out of the wall socket. If that was 120 volts DC, some things wouldn't work, but it would produce, it's the same amount of power.
Okay. Why did I hear that laughter? I mean, did I miss something?
Well, when you have a AC, the wave is going up and down, and that allows you to have a lot lower power contacts when you do DC. You have to have a lot more robust contacts because there's no zero.
Oh.
So there would be a pretty big difference on that.
Oh, yeah. Anything that required AC, like transformers, motors, wouldn't work on DC. Well, a universal DC motor, most transformer things wouldn't. And also, there was a big battle back in the early days between Thomas Edison and our friend Tesla and Westinghouse. Tesla used to work for Edison. Edison was big on DC power. He was trying to power New Jersey and everything with his dynamos. And Tesla was an AC guy. He even tried to do RF power transmission. He actually did it, these giant transmitter things, and he transmitted power a few miles, but it wasn't too practical. Anyway, he got pissed at Edison and left and went to work for Westinghouse, and they developed all the AC stuff, and that's sort of dominated because you have much less loss transmitting AC power over long distances on lines than you do DC. Well, that was the big reason, this power transfer. Anyway, that's history, not on the test.
The 0.707 is.
0.707 is what? 1 over the square root of 2. Right?
So if you have
A sine of 45.
a marine system, a lot of DC, or a solar system, a lot of DC, and you want to know why you're paying more for your breakers switches, because you have to handle a lot more,
That's why I don't have so.
Well, contacts will tend to weld on DC because the current's always going one way.
Yeah.
On AC, it kind of goes back and forth, so it's not as likely to weld the contacts. But
Ours is zero.
But I just got a 12-volt DC refrigerator freezer.
okay,
And boy, moving from an LP gas one, really nice.
okay. So the way we calculate RMS sine wave is we take the peak voltage, which would be 1/2 of the sine wave, and multiply that by 1 over the square root of 2, or 0.707, because it just happens to work out that if you looked at the area under the curve, okay, and you take this top above the 0.707 line on the chart and chop that off, and you flip this other half cycle up, that those two tops would fill in this missing area, and you'd have a straight DC equivalent power or voltage. Which is why it doesn't work out if it's not a sine wave. The numbers are different. If it was a square wave, it's simple. Flip the other half up, and it's whatever that is. Triangles and sawtooths, it's much more complicated.
And the perfect square wave doesn't exist either.
Sure. Don't have enough harmonics. So if we have the peak to peak voltage, we divide it by 2, right? To get the peak voltage, and then we do the RMS calculation. So and we've got an example here of this one. Yeah. Oh, we're doing average, which would be the square which was E squared over R. So we're doing volt RMS squared divided by R, or I squared times R, which are power formulas, which I guess are coming up next. But the two on the bottom, where voltage RMS is equal to the peak voltage divided by the square root of 2, or the peak to peak value divided by 2 times the square root. In other words, you take peak to peak voltage divided in half and then divided by the square root. Questions? You look puzzled.
I don't, Mike, that's the only look I got. Bob, see what I mean? That's the only look I got, Bob.
What value of an AC signal produces the same power dissipation or heat in a resistor as a DC voltage of the same value? Want to go with Charlie?
Charlie, yeah.
It's not peak, it's not peak peak. Okay. It's 0.707 of peak. 0.707 over 3 of 2 times peak. Peak. So what is the RMS voltage of a sine wave with a value of 17 volts peak? Half of the sine wave is 17.
Well, volts. 12 volts.
So we're going to multiply that by 0.707, right?
Yeah.
So about 3/4 of 17 is about what?
Alpha.
And it's definitely not 24 or 34. Oh, it's got to be smaller, right?
Yeah.
So your choice is 8.5 or 12.
One with alpha.
An 8.5 would be
Well,
Yeah. If you just round them,
yeah.
you don't necessarily need to do the calculator, and you can get close enough.
I was thinking cutting it in half. Now
We do the calculator, then you come up with 12.019.
Yeah.
So what is the peak-to-peak voltage of a sine wave with an RMS voltage of 120 volts? So it's kind of backwards. We want to know what peak-to-peak is if you know the RMS. Really?
And yes, this is the puzzle look at me.
Now, you feel free to use a calculator on this one. So,
Yeah.
what do we know? We know the peak, or we want to know the peak to peak voltage, right? And the peak to peak voltage is going to be 2 times the peak voltage.
Yeah.
And if we had the peak voltage, we know that's going to be the square root of 2 times the RMS value. And we know the RMS value. So if we plug all those things in, we can do 2 times the square root of 2 times the RMS value. And we get the 339.4 volts. They like to do these where they give you, they ask it one way and then they do the opposite.
Sounds like some other,
You have to work the formula both ways.
yeah, sounds like it's some other hooligan I know.
Everybody straight on that one? You can do it with a calculator, right?
Probably. It's been that long. So you got that slide rule handy?
Well, you can approximate square root of 2 by 1.5, make the math easy. And you still come out close enough. Okay, electrical power. I showed the pie chart in the technician class, which a lot of people find easier to remember Ohm's law. If you're not familiar with it, you know.
Oh, I'm familiar with it.
You basically put your finger over the quantity you want to find. Okay. So if I wanted to find power, okay, I cover up the P and it would tell me that it's going to be product of the current times the voltage. If I wanted to find the current, okay, it's going to be the power divided by the voltage. And if I wanted to find the voltage, it's power divided by the current. A lot of people find that easier to remember. And when they get on the exam, you turn the answer sheet over and you draw your little circle. I think if you can remember to do that, you'll have fun. Whatever helps. So power is the rate at which energy is used. And it was initially done in joules by one of them French guys and a Scottish guy named Watt, who is famous for steam engines and power. So he got power named after him, and we use the W, the watts, to represent the units of power, which is equal to 1 joule per second, which is a measure of energy per second. So the power in watts is going to be equal to the current in amps times the voltage in volts, just like on the circle. E is equal to I times E. If we go do some substitution of Ohm's law with Joule's law, we can come up with these other formulas. If you've got resistance, if you don't just have current and voltage. So it comes out that power can be represented as the square of the current times the resistance, or the square of the voltage divided by the resistance, or the product of the current times the voltage. So there's 3 different formulas, versions of the formula, and I just showed how you can derive all of them on the chart.
I'm so old, I remember when we used A instead of I,
Oh,
and it was real nice. It was just ear.
okay. So how many watts of electrical power are consumed if 400 volts DC is supplied to an 800 ohm load? So we have voltage E and resistance R. So we have to use one of those derived formulas. So which one will be used? E squared over R, maybe? So we know voltage, we know resistance. We want power. So if I got 400 volts, I square it. So I got 400 times 400 divided by 800. Let me show you how you can do it without the calculator. So if I take 400 and divide it by 800, that's 1/2 times 400. So 400 divided by 2 is 200. 200. Let's see if that's right. How about that? But you don't need a calculator for that.
Okay, I was wrong anyways.
And by
Oh,
the way, on calculators, sort of the recommended one is the TI 30 X2 or something like that. They're like $14 at Walmart places. Does all the scientific stuff. It's very easy to use. And it's solar powered. You don't have to put batteries in. You just have to give it some light once in a while. Okay. This is probably a hard one. How many watts of electrical power are consumed by a 12-volt DC light bulb that draws 2 amps?
0.2 amp.
Excuse me, 0.2 amps. So we know the voltage and we know the current. We want to know the power. We'll put our finger over the key. What do we get?
It's okay.
Which one? You think it's delta?
2.4 watts.
He's got an alpha? No. Huh? It's different. Call it Charlie. Charlie, alpha, delta? Yeah. We got a beta?
Why not? Let's run the
Why
gamut.
not? Okay. It's alpha, 2.4. 0.2 times 12. Voltage times current. Yeah, if you forget the decimal point, you get 24, and that's what.
Plug the wrong variable. Yeah.
How many watts are consumed when a current of 7 milliamps flows to a 1,250 ohm resistance? So we want to know power. We have current and we have resistance. And one a while back, we wanted power and we had voltage and resistance. This time we got current and resistance. So the formula is what? Power is equal to I squared R. Right? Right. So if you square 7 milliamps divided by 1,250 ohms, that would be the answer. So, and it's easy if you've got a calculator. If you're going to do it in your head, what do we do?
It's up and go.
Well,
Yeah, no.
see, I know you always had trouble with the units.
Yeah, I know.
So we're in milliamps, which is what? 10 to the minus 3, right?
Right.
And we have resistance in 1.2 kiloohms, right? 1.25, which is 1.25 times 10 to the third. So if I add 10 to the minus third times the 10 to the third, they kind of cancel out, don't
Yeah. Okay, smart guy, what is it?
So, but I've got a square 7, okay? So instead of 7 times 10 to the third, now we got 49 times 10 to the sixth,
Yeah,
okay? And I multiply that times 10 to the minus 6, excuse me. Then multiply that times 1.25 times 10 to the third. So I subtract 3, right? So it's now 49 times 10 to the minus 3 times 1.25, right?
right.
Which is approximately what? Well, the answer is something times 10 to the minus 3, right?
Right.
So it's going to be in milliwatts. So we
Yeah,
can get
so-
rid of the watts.
Yeah, I was just saying, that's what I was thinking. I just eliminated Bravo and Delta. I mean, that's what I was thinking. All right.
Okay. So
I'm gonna go with Charlie.
is 49 times 1.25 11 or 61? Which one do you think is closer?
I'm going with Charlie.
49 times
No, wait.
1.25.
No, you're right. I didn't bring in the 49. Yeah, that's,
Am I clear on that one? I squared times R for voltage, E squared divided by R.
that's for a second.
You have any questions, Amanda?
No, sir.
Did you follow that?
No, not really. Not this last one, but I'll catch up hopefully.
Can you hear us okay?
Yes, sir.
Okay. Well, here's another one for you. What's the RMS voltage across a 50 ohm dummy load dissipating 1200 watts? It doesn't matter that it's a dummy load. It's still 50 ohm resistance. So we know a resistance and we know watts. We want RMS voltage. Which really means we just want the volt. I think they threw the RMS in just to confuse you.
You're doing a good job.
So we know that power is equal to the voltage squared divided by the resistance.
Yeah.
Okay, we know the power and we know the resistance, but we don't know the voltage. So if we rearrange the formula, okay, if I multiply both sides by R, then I'm going to get power times the resistance is equal to square of the voltage, right?
Yeah.
So find the voltage, I want the square root of the product power times resistance. Now this is definitely easier on the calculator.
I think it's Bravo.
Probably approximated in head.
Bravo.
You think it's Bravo?
Yep.
You said Bravo? Got two Bravos.
I didn't calculate it.
Mine- Randy's working hard. Another Bravo. All right. So how did we get there? We took E is equal to E squared over R. Rearranged it so E squared is equal to P times R. So E is going to be equal to square root of P times R. And I did this on a calculator, but if you multiply 50 times 1200, you're going to get what, 60,000?
Yeah.
So it'd be 6 times 10 to the fourth, or square root of 6 times 10 to the 2. But whatever the square root of 6 is times 10 to the 2 is going to be something like 2.45 times 10 to the 2, or 244.95.
Yep.
Got 2.4,
Good enough.
244.4.
All right, peak envelope power. Byron, pay attention, you missed this one. Uh-oh. Or was it Ernie?
Yeah. You know, I think I was, as far as the law.
All right. What is peak envelope power? It's the maximum instantaneous power achieved when transmitting a phone signal. So down there in the chart, you see a modulation envelope. Kind of what it looks like when you speak into the transmitter, and that's how you modulate the carrier, what that waveform kind of looks like. So the peak envelope power is whatever the highest peak is in the envelope. And they use that for regulations. You're only allowed 1,500 watts peak envelope power on a lot of bands. And some of the technician bands, you're limited to 200 watts. There's a couple cases where they look at effective radiated power, which is different. It's the peak envelope power times the antenna gain and all those factors. So it's actually the maximum power radiated by the antenna.
Which would be more than 1,500.
Yes.
Up by how much, or does that?
It varies. I don't remember which one has the ERP restriction. A couple of them do.
Okay.
I'll refresh it when we get to that part in another section.
Okay.
I don't remember all this stuff from time to time, sort of have to review it. Okay, so when you have an unmodulated carrier, instead of seeing it, that envelope go up and down, it's just straight. You just you're transmitting a carrier when you're on FM, AM. And if there's no modulation, it's just straight. So the peak envelope power is going to be the average because all of those peaks are the same if you're not modulating. Now, they have a little exception there. It might be less with an SSB signal because with single sideband, you're not transmitting a carrier. You're only transmitting one of the sidebands. So if you're not talking, there's nothing. So you only see the real peak. So it's a little bit different. Pretty sure that's not a test question. Okay, so we know that the peak voltage is going to be twice the peak voltage, and that the RMS is going to be the peak voltage times 1 over the square root of 2, or 0.707. Because we already did RMS. Right?
Right.
So, and if it's peak to peak, and we just gotta divide peak to peak by 2 to get peak. So the peak envelope power is gonna be the VRMS voltage squared divided by resistance. So it's the old E square over R. So what is the ratio of peak envelope power to average power for an unmodulated carrier? Bravo. All right, you paid attention.
No, I read it in a book. My life depended on that moment.
Since it's not modulated, all the peaks are the same.
Yeah.
The average, is the peak envelope power. What is the output peak envelope power of an unmodulated carrier if the average power is 1,060 watts?
1,000.
Kind of a tricky question. It's what? Yeah, they make you want to think, well, it can't be that simple, right? It's still whatever the average power is if it's unmodulated. What is the PEP produced by 200 volts peak to peak across a 50 ohm dummy load? So we want power, we know voltage, and we know resistance. So it's back to the old E square over R, right? So we got 200 volts peak to peak, and we got to change that to peak voltage so we can figure RMS, right? So peak to peak is twice peak. So we divide it by 2, so we're down to 100 volts peak. And the RMS of 100 volts peak is about 70.7 volts, right?
Right.
Okay. But we got to square it. So what's 70.7 squared?
Say first. I'll say it's.
Well, I can approximate it and say it's, let's use 70. And if we square 70, it'd be 49 times 10 to the 2, right? Or
We know it's not.
Yeah. Yeah, you're right. That much I could surmise.
And that's an important thing to know on the test. Always want you to throw out your bad answers. You got it.
Oh, no, that's the one thing that Bob and Mike beat into my head during the technician classes. Eliminate what what's possible and what you know is, and I think there was one answer I remember that it was just the three of us. And it's like, these two numbers. Yeah. What are you thinking? I know it's not these two numbers. I know it, then it's, the last number, I think, it's like C or D. And
you
it's
can
like,
normally eliminate 2 of the answers easily.
yeah.
And then it's down to which of the other 2 is.
So I'm thinking it's Charlie.
You thinking it's Charlie? You just guessing Charlie, or you worked it out?
A little bit of both.
Okay. Got any other answers?
I'm gonna guess.
Okay, we got 2 Charlies, 3 Charlies, 4 Charlies.
Want to make it 5?
Well, I just looking at it without doing any calculating, I immediately thought of sounded like about 100 watts. I was trying to visualize the amount of,
Imagine that.
yeah.
Sometimes it helps not to overthink it.
Well, it does. What's
So we're 9 divided by,
I go back and think of how hot did a dummy load get when I was putting different,
490 divided by same as 5.
You're right. I was overthinking it.
That's one of the harder ones.
God, I hope it is the hardest.
Well, let's see, we're up to number 6 in that group. You only get one of these in this group. Of course, there's probably 3 hard ones.
Yeah.
What is the output PEP of 500 volts peak to peak across a 50 ohm load? It's almost the same question, and yeah, except it's 500 volts. And they didn't call it a dummy load. It's just Anybody got an answer?
I'll take a stab at it. I think it's
Remember, it's going to be the square of the RMS divided by the resistance, right?
right. Well, then maybe I won't. Okay, what is it?
I don't remember off the top. But I've already passed the test.
That you're already in.
Delta,
All right, Amanda, what was it?
delta,
Well, we got one delta. What else we got? Take a guess.
Yeah. I think
I'll show you
right.
the right answer. We'll figure out how you get there.
I'll go with Amanda. Delta.
2 deltas.
Now I'm gonna go with alpha for kicks and giggles.
Byron's going with alpha. You are a real rabble rouser. Well, let's see what we got. 625 watts. So how did we get there? We wanted to get down to RMS voltage, so we divide the peak to peak in half to get peak. And we multiply it times 1 over the square root of 2, or commonly known as 0.707. So that comes out to 176.77 volts RMS. We have to square that and then divide it by 50. Now I can't square that one in my head. We can probably estimate it. If you do it on the calculator, it'll come out 625 watts.
And that ain't for having changed the dangers.
As was on the previous question pool, Did you get that one, Amanda?
Yes, sir.
Okay, fun one, decibels. John likes decibels. Both love them to death. A decibel is defined as a base 10 logarithm of the ratio of two quantities. We normally use decibels to represent power gain, voltage gain, typically in units of dBi, which is decibel relative to the isotropic radiator, or a dBd, which is decibel relative to a dipole. That's what we use when we talk about antenna gains. In power, usually it's a dBm or a dB relative to a milliwatt. The formula is 10 times the log base 10 of some number divided by some other number ratio. When we're talking about power. If we were talking about voltage or current ratios, it would be 20 times the log of those values. Because if you remember, when we take the power formula and we rearrange it to get voltage or current with resistance, they're square functions, which is why it turns out to be 20 times if you're talking voltage or current. It's only 10 times the log when it's power. So, example for 3 dB, okay, example would be 10 times the log of ratio of 10 to 5, which is ratio of 2. Okay, and the log of 2 is 0.3, and 10 times the log, it's actually like 3.01. 10 times the log would be 3. So a 3 dB increase is a ratio of 2. If it was a minus 3 dB, it would be a ratio of 1/2. Right? Like, it would be like 5/10 in that example. So we'll skip the -1 for now, but it kind of wraps around. Didn't really have room to do it right. So the thing to remember is the 3 dB increase is times 2. A -3 dB increase is 1/2, or the reciprocal of it. 6 dB is times 4. -6 is 1/4, reciprocal of 4. 10 dB is times 10. -10 is a 10th. 20 dB would be times what? $100. So it goes up 30 dB, it's going to be the number of 0. 30 dB is going to be 1,000. 40 dB is going to be 10,000.
Just mathematic zeros.
60 dB is going to be 1,000,000. Right? If you got a 1500 watt amplifier on your radio, you're going to be putting out about 61 dB per milliwatts. Okay, just to give you an example. Okay, the other one, the -1 dB, that's one of the hardest questions on the test you might get. And they want to know what, if you have a 1 dB loss, what the percentage loss is. So the way you figure that out, you kind of have to do the anti-log. So you know that the minus 1 dB is equal to 10 times the log of something. So it's going to be minus 1/10 of the log of something. And the antilog is going to be 10 to the power of the log, which is how you find out what the something is. So x is going to be equal to 10 to the power of minus 0.1. Right? Because we took 1 and divided it by 10, the manipulations of the formula. So 10 to the minus 0.1 power, if you need a calculator, is going to be 0.794, or 79.4%. Okay, but they want to know the loss, so you have to subtract that from 100. So it's slightly over 20%. So a 1 dB loss is a 20% loss, which is a lot more than I expect. Because we tend to say a 1 dB loss is negligible. It's not really that negligible. And if you're talking about doing really weak signal stuff, a moon bounce, it's really significant. So hopefully you don't get that question, but just remember that it's 20%. You don't have to work.
And I'm gonna throw in a weird,
Okay.
because we're generally not using directional antennas. You actually have to quadruple your power and double your effective range or distance.
Because of the square law.
Powers radiating out in all directions. So if you want, if I'm running 5 watts, by 20 watts, I've effectively doubled my range. If I go up to 80 watts, I've effectively doubled it again. And then if I turn up to 320, again, I'm basically going to 1300 watts around there. So that QRP, I'm basically units down the legal limit stage.
And an S unit is approximately minus 6 dB or 60. Okay. So what dB change represents a factor of 2 decrease in power? So twice the power or half the power is how many dB? Plus or minus
3 dB.
Yeah.
Okay, 3 dB. You work with those and it's just, 3 dB is 2 and 6 dB is 4.
And my cell phone signal is neg 88 dBm right now in this room.
Thanks for sharing.
Useless.
Okay, and here's the one you'll dread. What percentage of power loss is equivalent to a loss of 1 dB? We all know the answer to that one. Weren't you paying attention?
I was.
What's the answer?
Why is everybody looking at me now?
What's your answer?
My answer is Charlie.
Charlie.
There you
Okay.
go.
All right. And then go
Are
to
you
all the
paying
calculations again. Just have to remember, if you want to do the calculation, how to do the anti-log. So it'd be 10 to the power of the log. And since it's 10 times the log, and that's where the divide by 10 comes in. All right, series parallel circuits. I don't know how to move that bar. So, what did we learn? Series and parallel resistive circuits that In series, the total current's the same through each component. In parallel, the total current equals the sum of the current through all of the legs, branches. We learned that our root mean square of a sine wave is the value of an AC voltage that produces the same power dissipation as a DC voltage of the same value. So 120 volts RMS would be the same power into a load as 120 volts DC. Power is the rate at which energy is expended. So it's either the product of the voltage times the current, or the voltage squared divided by the resistance, or the current squared times the resistance. So you need to remember all three of those, because all three versions of those are questions on the test, but you'll only get one of them. You just don't know which one. Peak envelope power is the maximum instantaneous power when transmitting a phone signal. So it's the peak power in that envelope of the modulated waveform. If it's unmodulated, then you've got a constant carrier waveform, so the average power is the peak envelope power. And in dB, it's the logarithm of the ratio of two values. It's 10 dB times the log of that ratio of power, 20 dB times the log if it's voltage or current. And 3 dB is times 2, 4 dB is times 4, 10 dB, 6 dB is times 4, 10 dB is times 10, 20 is 100, and on up, keep adding zeros. Any questions on those?